In this module, I am going to cover structures. All of you have definitely used structures in other programming languages, so as in earlier cases, let us jump at coding examples and focus on its implementation in Swift. Let me first describe a few features in the context of structures and classes. Both structures and classes in Swift have lots of commonality. In this lesson, I am going to talk on structures. Whatever I discuss here also applies to classes that you will learn in the next lesson. Structures have properties. Properties are similar to attributes in other languages. These are used for storing values. Structures can contain methods, which are useful in defining its functionality. These are basically the functions that we covered in the earlier lessons, except that they are now enclosed within the scope of the structure and are not global as in earlier examples. Structures in Swift allow you to define subscripts to provide access to their values using subscript syntax. Initializers are similar to class constructors in other languages. I will describe the differences when we look at some code later in this module. Of course, you have deinitializers too in Swift. They have the purpose of destructors in other languages. Structures can be expanded to increase their functionality beyond the default implementation. I will be covering this in Advanced Swift. Structures can conform to protocols to provide a standard functionality of a certain kind. We will cover this in Advanced Swift. Let us now jump to an example of a structure. This example declares a structure named complex. The structure itself is declared using the struct keyword. The complex structure defines two properties. Both properties have data type of double and are declared as variable properties. Thus, their values can be modified by your code. You may also declare constant properties with the keyword let. You will create an instance of complex structure in your program by calling its constructor. In Swift terminology, this is called initializer. Note that we have not defined any initializer in our structure definition. When you do not provide any initializers of your own, the compiler provides its own default initializer to set the values of its properties. Note that the two parameter names shown here are same as the corresponding property names. It is mandatory to include these external names when you call the initializer. Omitting them generates a compile time error. This statement modifies the value of real property. You can verify the modifications by printing the property values in a print statement. We will now add a method to our structure definition. The methods are added to the structure using a function declaration. Here, we declare a function called add. The function takes another complex instance as a parameter and returns an instance of complex to the caller. In the function's body, we simply return a complex instance. The instance itself is constructed by calling the compiler-provided initializer with some computations to deduce the addition of two mathematical complex numbers. To call this method, we use the above code. First, we declare variable C1 of complex type and print its properties on the console. Similarly, we declare C2 and print its properties. We now call the add method on C1 instance and pass C2 as a parameter to it. The returned value is assigned to a constant called C3. We validate the contents of C3 against our expectations. Now, I will describe how to write custom initializers for your structure. The complete code for our complex structure with 3 custom initializers added is shown here. The first initializer does not take any parameters and in its body sets both real and imaginary properties to value 0. The second initializer takes one parameter called real. In the body, it copies the parameter value into the property value. Note that both parameter and the property have been given the same name. To distinguish between the two, we use self keyword. The self.real refers to the property variable and just the real term refers to the method parameter. The imaginary property is then set to a value of 0 in the second statement. In the third situation, the initializer takes 2 parameters and copies their values into the 2 respective properties. The functionality of this initializer is same as the default one provided by the compiler. Remember that the compiler provides a default initializer only if you do not provide any initializers of your own. Even if you provide a no-parameter initializer, the compiler would not provide its default initializer and our add method would then generate a compile time error. Therefore, the last 2-parameter initializer was required to be defined in the current scenario. Earlier, I just mentioned that when you pass structure objects around, those are passed by value. I will now briefly illustrate this with an example. We first declare a variable C1 of complex type using no argument initializer. Thus, both real and imaginary properties of C1 will equal 0. We now create another variable C2 and assign it to C1. When you do so, all stored properties of C1 will be copied into C2. The variable C2, though is the same structure as C1, will hold an independent copy of all the properties of the original C1. Verify this by modifying the real property of C2. When you print the values of C1 and C2, you will observe that the real property of both variables are now different and thus independent of each other. In Swift, strings, arrays, and dictionaries are implemented as structures, so when you pass them around and make copies of them, is lots of memory space wasted? Swift provides optimization by performing an actual copy behind the scenes when it is absolutely necessary to do so. Those who know Objective-C, note that the equivalent types, that is NSString, NSArray, and NSDictionary, are implemented as classes and they are thus passed by reference holding a single copy of data in memory. I will now discuss a few important features related to structures. If you create a structure instance and assign it to a constant, can you modify its properties? The answer is no. Consider these 2 program statements. The first statement creates a complex instance whose properties are modifiable. The instance is assigned to a constant. In the second statement, when you try to modify the property, it generates a compile time error. Swift allows you to create read-only properties in a structure. The values of such properties are computed in the property definition itself. I will show you how. Consider the definition of circle shown here. The radius property is assigned some default value. Next, we define a property called area of type double. We follow the declaration with an opening and closing curly braces. Within the braces, we write a program statement that computes the area of circle and returns its value. Who uses this value? I will explain this shortly. Next, we declare one more property called circumference that computes the circumference of the circle. This too is a read-only computed property of the circle structure. Now, let us study how to use these properties. We first create an instance of circle. We print the value of radius property by using the string interpolation. We print the value of area property just the way we did it for radius. Whenever the program accesses a read-only property, it will compute its value by executing the code in its definition. Similarly, we call myCircle.Circumference to get the value of circumference property and use it in the print line statement. Now, try by changing the value of radius property and print the two computed property values. You will see that the values are indeed modified as expected. The program output is shown here. I will give you another practical example of read-only computed property. Consider a situation where you have stored RGB components of color in a structure type. You would like to add a property to it that represents the hex string corresponding to RGB values. In this example, we declare a structure called color. The property called RGB holds a tuple consisting of three integers corresponding to red, green, and blue components of the color. The property called value is of type string. In the body of the property definition, we write a function called get. The get function returns in hex formatted string to the caller. You may add any number of functions like this in the property's definition. Like a get function, you may write a set function that allows you to set the property value. I will talk about this in more details very soon. We use the structure in our code as shown here. We construct an instance of color structure and assign it to a variable called rainbow. We set the RGB property to a new value. When you print this value, you will see this output on the console. In the last example, you saw how to add a get function to a property. Now, you will learn to add a setter that allows you to set a value for the property. We will now rewrite the definition of color structure. We declare three variables for storing RGB components of the color. We now declare a variable called RGB of type tuple that consists of three integer values. The get function constructs a tuple containing the three component variables and returns it to the caller. Now, let us look at the definition of set method. In its body, we set a local variable red to a new value. The right-hand side of the expression specifies the value as newValue.0. The new value is a tuple that we want to assign to RGB. The variable name for the tuple is newValue. This is implicit. I will show you later how to set an explicit name for the parameters passed to the set function. The newValue.0 specifies the first element of the tuple. This is assigned to the variable red. Likewise, we will assign the second and third elements of the newValue tuple to green and blue variables. Now, I will show you how to use these getter-setter methods. First, we create an instance of color structure. Next, we assign some value to it. The value assigned is a tuple. Note that in the body of the setter function, this tuple will receive an implicit name newValue. The assignment results in setting the three component variables within the color structure. Here, we use the get function to retrieve the value of RGB variable. Note that my color variable will automatically be of tuple type consisting of three integers. As you know, this is inferred from the assignment. The next statement simply prints the three elements of the received tuple. Now, I will describe typed properties. You have used static keyword in other languages. In Swift, when you associate the static keyword with a property, it is called a typed property. A typed property is associated with the type and its value is retained across all its instances. I will now give you a trivial example of a typed property. We create a step counter that keeps track of the number of steps taken by an athlete. Each athlete will have its own exclusive step counter. We will also create another counter that maintains the count of steps taken by all athletes together. The global counter structure declares a variable called value of type integer with an initial value of 0. Note that we have prefixed the declaration with the static keyword. This variable is now available to any other code without creating an instance of global counter structure. The step counter structure declares a variable called steps with an initial value of 0. Whenever the value of steps variable is set, we increment the global counter in the didSet callback method. Note that we do not create an instance of global counter to access the value property. Now, somewhere in your program code, you would create two instances of step counter. The first instance takes 2 steps and second instance takes only 1 step. Both instances would also modify the global counter internally. We print the values of steps taken by 2 instances and also the global count that tracks the total number of steps. When you run the program, you will see the output shown here. Note that the global count gives the total number of steps that correctly reflects the total of steps taken by 2 counter instances. As structures and enumerations are value types, their properties cannot be modified from within its instance methods. Methods intending to modify the properties must be declared with mutating keyword prefix. I shall illustrate this with a trivial example. Consider the definition of jump counter shown here. The structure defines a variable called steps of type integer with an initial value set to 0. Now, we want to write a function called increment that would increment the steps by a factor specified in the function parameter. In the body of the increment function, we add the input parameter value to the steps variable. However, this statement would generate a compile time error as the structure variables cannot be modified within its own methods. Prefixing the function declaration with the mutating keyword would remove the compile time error. You can test the effect of calling a mutating function with the code fragment shown here. We create an instance of jump counter. This statement modifies the steps variable directly. Here, the increment function modifies the contents of steps variable. When you print the value of steps variable, you will see this output. In the next module you will be studying classes. As classes are reference types, you do not use the mutating keyword for methods defined within a class. The class instance methods are able to modify the class instance variables without the method being declared as mutating. All the features that we have seen so far also apply to classes that I am going to discuss in the next lesson. Both structures and classes also provide features such as property observers. Rather than prolonging this lesson, I shall describe these and other common features in the context of classes in the next lesson. So let us proceed to classes. Hope you like this module. Over the past several years of iOS development, we have deployed many apps in the App Store. Like this course, many of these apps are free to download. Do visit the URL mentioned here to download and try out these apps. Thank you for supporting our development. Now, As you have completed this module, you will definitely like to look up other modules in this course. Do visit the above URL to get links to all other modules in this course.